Example 2, we consider a point in the structural member that is subjected to plane stress. Okay, this term appears again. The plane stress means that you do not have any stress along the z direction. If we're considering xy plane, the plane stress means that you do not have any stress along z direction or on the z plane. Okay, so normal and shear stress acting on the horizontal and vertical planes, the x and y planes at the point are shown in the figure. Then determine the principal stresses and the maximum in-plane shear stress acting on the point. Okay, this is easy. This is the same as example 1. But look at the step C, to compute the maximum absolute shear stress at the point. Here comes a new concept called maximum absolute shear stress. What does that mean? Okay. To determine the in-plane stress, we can just use a basic Mohr circle, one Mohr circle, like what we did in example 1. You can solve the problem. But how about absolute shear stress, maximum absolute shear stress, meaning that although you do not have stress along z direction, but you may have a larger stress, shear stress, out of the xy plane. Do you think that is possible? If you can find a maximum, if you can find a larger shear stress out of the xy plane, meaning that the maximum shear stress in the xy plane is not the maximum absolute shear stress. So you need to find another bigger values and the maximum possibility of the absolute shear stress out of the xy plane. Okay, let's look at some details. So to solve this type of problem, we need to use three-dimensional Mohr circle, okay, which is composed of 3 basic Mohr circles. Okay, so in this case, you can see that you have a 3-dimensional stress element. But as we said, if we consider a plane stress situation, so your sigma z equals 0, and sigma xz equals 0, sigma yz also equals 0. Okay, this is plane stress. So let's analyze 3-dimensional Mohr circles in 2 scenarios. Okay, in the first scenario, let's consider in xy plane the two stresses, sigma x times sigma y, both larger than 0, or principal stresses, both principal stresses, sigma p1 times sigma p2 larger than 0, meaning that both of them larger than 0 or both of them smaller than 0, both of them positive or both of them negative. Okay, they're the same sign. Okay, let's see, sigma x times sigma y equals 0, or more strictly speaking, it should be sigma py times sigma p2 larger than 0. Okay, so here is a 3-dimensional stress element. We have more than xy planes. Okay, since here you have also zy plane and xz planes. Okay, so here we assume that sigma z equals 0, and all of those taus are 0. All of the shear stresses are 0. Okay, and in this 2-dimensional xz plane, we set sigma x equals 14, sigma y equals 4, then the tau xy equals 0. Okay, so this is a status of a plane of a principal stress. Okay, since you have the 2 principal stresses and tau xy equals 0. Okay, so let's analyze the in-plane stresses on the xy plane first. Okay, let's draw a Mohr circle for the xy plane. At this xy plane, so you have these 3 components. That is 14 along x direction, 4 along y direction, and tau xy 0. Okay, to draw the basic Mohr circle for the xy plane, first of all we need to find these 2 points, right? Two normal stress point is 14 and 4. Okay, let's see. Here's the 14 and 4. Then let's look at the other 2 points we need. That is the 14, 0 and 4, 0. Right? Still the same 2 points. Okay, this connect these 2 points. We get a diameter. Then use this as diameter. We draw the Mohr circle. We got this blue circle. Okay, this is the first Mohr circle, basic Mohr circle on the xy plane. Okay, of course, based on this, you can determine the maximum shear stress. That is here. Right, so you get this is tau max xy. Right, this is tau max on xy plane, and that is 5. Okay, but as we said, if you consider 3-dimensional, then you have 2 other planes. Right, this is YZ plane and XZ plane. Okay, if you look at the YZ plane, the green colored YZ plane, that would be here. Okay, this is the YZ plane, green colored YZ plane. If you look at this YZ plane, you will have sigma y, right? Sigma y equals 4 and sigma z equals 0. Okay, again, they do not have any shear stress, so tau yz and tau zy both equal 0. Okay, so you can draw another Mohr circle, basic Mohr circle, based on the YZ plane. Okay, the first point YZ is 4 right here, and the second point 0 here. Tau equals 0, right? So you get a 4, 0, 0, 0. You get these 2 points and connect them. You get the diameter. So you can draw another Mohr circle. Right, this is the second Mohr circle for YZ plane. Okay, so here you can see that the diameter is 4, so the radius is 2. So the maximum shear stress here, right, is a tau max YZ equals 2. Right? Then we have the third plane that you can examine. Well, here is the third plane, XZ plane. Okay, on the XZ plane, the red colored plane, let's use the red color to see. Here is the XZ plane. Okay, on the red colored XZ plane, you have sigma x equals 14 and sigma z equals 0, and tau xz, tau zx both 0. Okay, so based on this, you can draw the Mohr circle. And the first point, sigma x, 14 here. Second point, 0 here. And their tau components are both 0. So just to connect these 2 points to get diameter. The diameter is 14, right? So you can draw another Mohr circle, basic Mohr circle. I'll get an ugly one, but this is the largest Mohr circle, okay, for the XZ plane. Okay, so on this XZ plane, so you can easily determine that the diameter is 14 and the radius will be 7. So here you get the tau max on the XZ plane. So that is 7. Okay. So you got 3 maximum shear stresses. So which is the biggest one? Which is the largest value? Obviously, that is the tau max xz, right? That is 7. So this is called the absolute maximum absolute shear stress. Okay, if you only look at xy plane, the in-plane max max shear stress will be 5. Okay, so this is the difference. If you do not look at other planes, if you only look at xy plane like what we did in example 1, so that is called the maximum in-plane shear stress. So your result will be 5. But if you're looking at the absolute maximum shear stress, you should draw 3 Mohr circles, 3D Mohr circle. Then you can analyze that. Well, in this scenario, you get the maximum value here is 7. Okay, so this is only valid in this scenario where your sigma p1 times sigma p2 is larger than 0, meaning that they are both positive or they are both negative. Okay, so let's summarize this. If you have sigma p1 times sigma p2 is larger than 0, then the maximum in-plane stress shear maximum in-plane shear stress will be sigma p1 minus sigma p2 over 2. Right, that is the radius of the blue circle. Okay, so if you're looking at the absolute maximum shear stress, right, so that will be larger. So that is half of the sigma p1. Right, since your diameter is just sigma p1 minus 0. Okay, so the radius will be half of the sigma p1, the largest possible normal stress. Okay, so here you get these two cases. In plane, absolute. If this is scenario 1, then we will have another scenario, that is scenario 2, in which your sigma p1 times sigma p2 smaller than 0. It's negative, meaning that you have one of them is positive, one of them is negative. Okay, one in compression, one in tension. Okay, so in this example, we will just consider that the stress along x direction, normal stress along x direction is larger than is positive, and the normal stress along y direction is negative in compression. Okay, so here is the example in which let's set the sigma x equals 10, sigma y equals negative 3, and the tau xy equals 0. Okay, this is the stress status on the xy plane. Okay, again, we can draw the first basic Mohr circle. Okay, so the first step, we find the sigma x and sigma y on the sigma axis. Sigma x is 10. 10 here. Sigma y is negative 3 here. Okay. Then we find the 2 points, sigma x tau xy, that is 10, 0, right? This is still this point. And the second point will be sigma y negative tau xy, negative 3, 0. Okay, this is these 2 points. So connect them, you get the diameter, then use it to draw the blue circle. Okay, this is the first basic Mohr circle for xy plane. Then again, we have the other 2 planes to analyze. So first of all, let's look at the green colored YZ plane. This is the green colored YZ plane. I see on this plane, you have sigma y, that is negative 3, and sigma z, is 0. Okay, so find this 2 point first. -3, 0. Then connect them. Of course, here's the tau yz equals 0. Okay, so you do not need to find other 2 points above and below the sigma axis. You just need to connect these 2 points directly and then draw the Mohr circle. Okay, so this is the Mohr circle for the YZ plane. And let's look at the XZ plane, the red colored XZ plane, the top plane right here. Okay, on this plane, your sigma x equals 10, sigma z equals 0, and tau xz equals 0. Okay, find the first normal stress, 10 here, and the second normal stress, 0 here. Then the other 2 points will be 10, 0, and 0, 0. Okay, so connect them together, you get the diameter, then you can draw the Mohr circle. Okay, you got the Mohr circle for the XZ plane now. Okay, so here you can see that you have again three Mohr circle, basic Mohr circles to form the 3D Mohr circle in this case. So what is the tau max xy? Tau max xy. The maximum shear stress on the xy plane. What is it here? Right. It's right here, and so its coordinates will be. Let's see here. You have 10, -3. So the R is 6.5. So this point you will have 3.5, 6.5, right? So the maximum shear stress on the XY plane will be 6.5. And how about the YZ plane? On the YZ plane, you have 0, 3. So here you will have -1.5, 1.5. Okay, so the tau max on the YZ plane will be 1.5, and the XZ plane. Okay. The red colored XZ plane, you have here the point coordinates will be 5, 5. Okay, so the tau max on the XZ plane will be 5. Okay, so you can see that if we consider the XY plane, the in-plane maximum in-plane shear stress will be this 6.5. And what is the maximum absolute shear stress? It's also here. Okay, also this one. Okay, so in this case, if your two principal normal stresses have opposite signs, their products is smaller than 0, then you can see that the in-plane maximum shear stress and the absolute maximum shear stress will be the same. Okay, to summarize this, you can see that if the sigma p1 times sigma p2 is negative, meaning that they have different signs, then the maximum in-plane shear stress and the maximum absolute shear stress will be the same, and their values will be both sigma p1 minus sigma p2 over 2. Okay. So knowing this, let's go back to example 2 to solve the maximum in-plane shear stress and maximum absolute shear stress. If you know that, let's list all of these initial stress components. First of all, so here the sigma x is negative 62. Sigma y is negative 94. Tau xy negative negative 42. Okay, so here just using these values, we can draw a Mohr circle. Okay, the first point will be negative 62. And the second point is negative 94. Then these 2 points will be the first point sigma x tau xy, negative 62, negative 42. Okay, here. And the second will be sigma y, negative tau xy. You get a negative 94, positive 42. Okay, then we will connect these 2 points. Then use it to draw a Mohr circle. You got the first Mohr circle. Then here you can identify those critical points. The center will be negative 78, 0. Right here is negative okay, the C here is just negative 62 minus 94 over 2. So you got negative 78. And the R is negative 62 plus 94 over 2 square plus 42 square root. And the result will be 45. Okay, so the principal stresses will be sigma p1 equals negative 78 plus 45, you got negative 33. Sigma P2 would be negative 47 minus 45. Negative 78 minus 45, you get negative 127. Okay, so those are the 2 points. Negative 33 and negative 123. Okay, so the in plane maximum shear stress, tau max in plane, will be just R, right? So it's 45 MPa, and it can be positive or negative, right? Then how about the maximum absolute value, maximum absolute shear stress? It is here you can draw another basic Mohr circles. So the one of them will be here. Just find the negative 33 and 0. These are two principal stresses on the green plane. Will be here. And the other one will be connecting this one and this time the original point and the sigma P2, right? Then you can get another bigger Mohr circle. While here the R will be 0 minus negative 123 over 2. You got 61.5, right? Meaning that the maximum absolute shear stress is 61.5 MPa. It can be negative or positive. Okay. So this is how did we solve this one. This is maximum absolute shear stress using a Mohr circle, 3D Mohr circle. But if you know this theory, and you can judge it quickly, since in this case the sigma P1 and sigma P2 are both negative. Okay, so their product will be positive. So you should use these equations. Okay, when their product is positive, then their maximum in plane and maximum absolute shear stress will be different. Right, so you can see that this result, if you use these equations to calculate these two values, you will get the same result as we just analyzed through drawing the complete 3D Mohr circle. Okay, here are some extensions of example 2. So you can try to determine this maximum in plane and maximum absolute shear stresses. I have given you the answers. You can try to calculate them by yourself. Then let me know if you can get these results, the same results. If you cannot, let me know so I can give you the whole process. And here's the example 3. The example 3 is an in-class assessment. Okay, this is your in-class assessment. Okay, just solve it and submit it to Canvas. Okay, so here the Mohr circle is shown for a point. Then one grid telling you that here the one grid is 7 MPa. and here is also 7 MPa. Okay, determine the maximum in-plane shear stress and the maximum absolute shear stress. Okay, to determine the maximum in-plane shear stress, what you need to do is just counting the number of grids. Right? Obviously, just here, start from here to the top. Okay, so you can count how many grids you have. So 1, 2, 3, 4, 5, 6, 7, 8, 8.5, around that. Okay, so you get 8.5 grids times 7. So you get the tall max in plane. Then you need to think about how to determine the maximum absolute shear stress. Okay, this is your task.